So you got this rod hanging from a string. You got a couple objects on either end of the rod. We're going to call the first, let's call it object number 1 over here this time on the right-hand side. It doesn't really matter, right? It's got a certain charge. We'll call that charge Q. We bring another charge, Q2, nearby it. That's going to be represented by my fist. When Q2 goes nearby that, it's either going to attract a little bit or it's going to repel a little bit. In other words, there's going to be a little bit of twisting in that string, a little bit of twisting in that string as a result of the torsional properties, the twisting properties of the string. This is what we call Coulomb's torsion balance experiment, or Coulomb's twisting string balance experiment. When we bring these two charges close together, there is a force, and we can measure the value of some of those variables to determine the relationship between that force, the values of the charges, and the distance that separates the charges. We got to measure a few things, though. R, that's the easy one, because we're just going to use a ruler. Q1 and Q2, well, we can't measure those directly. So how are we going to measure them if we can't measure them directly? We can't say that it's 6.3 times 10 to the negative 12 coulombs. How can we measure Q1 and Q2 then? Let's deal with the relative values. The relative values. So in other words, if we had Q, if charge number 1 is Q, and then we want to change that value, we want to manipulate that value, then let's touch it against something that's neutral. Then it becomes a half Q. And then let's touch it against something that's neutral again. Then it becomes a quarter Q. And then let's touch it against something that's neutral again. It becomes an eighth Q. So we don't know what the actual charge of Q1 or Q2 is for that matter. But we can determine what it is relative to what it was the last time. So we can manipulate the value of Q without actually knowing what the value is to begin with. Which is okay, because all we're trying to do here is establish a relationship, not to establish a number for a constant or anything like that. Measure the value of Q1 and Q2, at least the relative values. And we can measure the value of the force, the magnitude of the force, by looking at the amount that the string twists. Twist 3 degrees, got to be this much force. Twist 8 degrees, got to be this much force. Perform 3 experiments. The first experiment would be an experiment in which we would end up plotting a graph of F versus Q1. What's the manipulated variable there in that experiment? Yep, Q1. What's the responding variable in that experiment? Katie, what's the responding variable? Good, Q2. And what, sorry, no, not Q2. What's the responding variable? Force. The manipulated variable is always on the x-axis, responding on the y-axis. So force is the responding variable. What would be my control variables there? What do I got to keep constant in that experiment in order to see what effect manipulating Q1 has on F? What stays the same? Cool? No. What are the control variables? Control variables. Q2 and R. Good. Now, when I plot that graph, I should get a straight line graph. That tells me that F is related to Q1, or F is equal to something times Q1. Something times Q1. What times Q1? Don't know right now, but it's equal to something times Q1. Next, we do the second experiment, where we end up plotting a graph of F versus Q2. Cole, what's the manipulated variable in this one? Good. What's the responding variable in this one? Dallas. Good. What are the control variables in this one, Tyler? Good, Q1 and R. We plot a graph of this one, we get a straight line again. That tells us that F is related to Q2, or F is equal to something times Q2. Next one we plot F versus R. What's the manipulated in this one? Yep, R, good. What's the responding variable in this one? Responding variable is always the same in these experiments, right? Georgia, what's the responding variable here? Good. And what are the control variables here, Cassie? Good, Q1 and Q2. Those are the ones we've got to keep the same. Now we plot a graph of this one. Works out to be a curved line downwards like this. Now, mathematically, you see a graph like that, it could say F is equal to something times 1 over 1 over R. Or it could say F is equal to something times 1 over R squared. We actually have to do something with this graph in order to determine which one it is. As it turns out, it's the second one. F is equal to something times 1 over r squared. So what Coulomb does now, takes a look at this and says, hey, wait, I got the relationship between F and Q1, Q2, and R. Let's just put them together and say F is equal to something times Q1, Q2 times 1 over r squared. That something is a constant that we call Coulomb's constant, K. And its value, as we saw yesterday, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Now, you might not remember from physics 20 the value of big G, the gravitational constant. We mentioned it yesterday, but you still might not remember it from yesterday. That's okay. Check your data sheet. Look at the value of big G, if you don't remember what it is, that is, and compare it to the value of Coulomb's constant here, K. Bigger, smaller? Yep. K. So we're looking at K as compared to big G. K is way bigger, isn't it? K is way bigger. The electrostatic force of attraction or repulsion is nearly always bigger than the force of gravity. We think of gravity as being a really big force. It isn't. In the grand scheme of things, there's 4 fundamental forces in the universe. And in the grand scheme of things, gravity is a really, really, really small force. We just think of it as being big because we're so used to experiencing gravity in the context of the Earth, which has such a big amount of mass. If we're dealing with more normal objects, more normal objects like you and me, force of gravity between you and me is minuscule, right? Virtually immeasurable because the masses are so small. The force of gravity only becomes significant when you're dealing with really, really big masses like the Earth, like the Sun, and so on. All right. We had one question for homework last night. Page 530, question number 1. Any issues with that question? No? It's all good? One word of caution, a couple words of caution here. Number 1, we're dealing with a positive charge and a negative charge here. Okay, we got the charge of a proton, which is the charge of the nucleus of the hydrogen atom. And then we've got the charge of the electron, which is negative. So we got a positive and a negative. It's a good idea to circle the positive and the negative because you might forget that we're dealing with a positive and a negative. And it's kind of important. But it's not important that it's a positive and a negative when you're plugging the values into an equation. We drop the sign of the charge whenever we're plugging it into this equation, or any other equation for that matter. We only put the magnitude of the charge. For us, when we're plugging numbers into an equation, positives and negatives mean direction, not a type of something, not what kind of charge you have, but rather direction. Okay, this positive and negative don't mean direction at all. So drop the sign when you're plugging it into the equation. Why did I circle it then? Why was it important to still remember that there's a positive and a negative charge here, even though we're not going to put it into the equation? Good. You're asked for the electrostatic force. Force is a vector, it includes direction. So we have to know whether it's an attractive force or a repulsive force. And the only way to determine that is to look at whether it's like charges or opposite charges. Here we've got opposite charges, well, we have equal and opposite charges here, although they don't have to be equal and opposite. One's positive, one's negative, regardless of the values, then we'd say it's an attractive force. All right, let's take a look at another example here on page 531. It says 2 spheres in example 10.1, that's the example we did yesterday, are momentarily brought together, then return to their original separation distance. What's the electrostatic force now exerted by one charge on the other? Well, let's go back to example 10.1. And let's look at what the charges were. It's negative 2.1 times 10 to the minus 6 and positive 1.5 times 10 to the minus 6. The separation distance was 3.30 centimeters. Listen, if we're dealing with the same charges in the same distance, isn't the force going to be the same as in the last example? Isn't this just a repeat of the last example? What's different about this question than 10.1? 10.1 said, here's a charge, here's a distance, what's the force between them? What's different about this one? They touch each other. So what? Good. If they touch each other, charges should balance. This is two questions, really, right? There's the touching, which we've done before, and then there's the force, which we've also done before. We've just never done those two questions together. That's what we're going to do right now. Touch them together, balance them, as Dallas said, and then we're going to find out what the force is now after they touch each other. So once these guys touch each other, what do they become? Well, we're going to say negative 2.1 times 10 to the minus 6 plus 1.5 times 10 to the minus 6 divided by 2. So they both become, what is that, negative 0.6, negative 0.3 times 10 to the minus 6, or negative 3.0 times 10 to the minus 7 coulombs. So now they're both negative 3.0 times 10 to the minus 7 coulombs. Brought back to their original separation distance, 3.3 centimeters. (8.99 times 10 to the 9) times Q1, which is 3 times 10 to the minus 7. We're dropping the negative there, right? Not the negative exponent. Never do that. The negative in front of the base, because that's just telling us what kind of charge we have. Could I have simplified that a little bit when I wrote that down? How could I have done that? Yeah, I could have just went 3 times 10 to the negative 7 squared, right? Since it's the same value. And we go 0.03 meters, or 3.3 times 10 to the negative 2 meters. And don't forget to square that value either. Let's figure this out together here, guys. We got 8.99 times 10 to the 9 times 3 times 10 to the minus 3 times 3 times 10 to the minus 3. Minus 7, you're right. 10 to the minus 7. 3 times 10 to the minus 7. Let's press equals. That's the number on the top. That's the numerator. Now let's divide that by the denominator. Let's see some brackets here. 3.3 times 10 to the minus 2. And then let's square that, everything inside the brackets. And we get 0.72743. But I think it should be rounded to 2 digits, 0.74 newtons. Now, attractive or repulsive? Force is a vector. We need to know. Attractive or repulsive, Braden? Attractive. How do you know? Oh, or are they? Is it attractive? Hayden? They're both negative now, right? Braden, after they touch each other, they both become negative, right? So this is going to be a repulsive force. So listen to this. What I'm saying here is this. Two objects attract each other, right? You got a positive and you got a negative. They attract each other. Then they touch, and then they repel each other? Yeah, that's what happens. Two objects attract each other, they touch together, the charge is balanced, they become like charges now, and now they're going to repel each other, right? Good? Let's see what we can do with this question over the next, we'll give you 3 or 4 minutes to see what you can get done with this one, okay? Let's try one more example here, guys. This one's a little bit different, similar in some ways, but different in some ways, a little bit more to it. This one says a small metal sphere, sphere B, has a negative charge of 2.1 times 10 to the minus 6, and it's placed midway between two other spheres that are 3.3 centimeters apart. Ooh. We got sphere B, sphere A, and sphere C. Sphere A and C are 3.30 centimeters apart. Sphere A has a charge of positive 1.0 times 10 to the negative 6 coulombs. Sphere C is positive 1.5 times 10 to the minus 6 coulombs. And sphere B in the middle is negative 2.1 times 10 to the negative 6 coulombs. And we want to find, what do we want to find here? The net electrostatic force on the negative charge. The net force on charge B here. Yeah, I have an idea for this. Can we do F is equal to K Q1, Q2, Q3 over R squared? Can we just modify the equation a little bit and add the third charge in there? Think that's okay? Alice, why not? Okay, you're not on the same side. Okay, fair enough. Okay, subtract the two forces, okay? Yeah. So you can say Q1, Q2, Q3 over R squared? Okay, because they're all on the same line, okay? Anybody else, yes or no? You can't do that. You can't do that, and the reason you can't do that is because it messes up the units, right? If you multiply K, Q1, Q2 over R squared, and that gives you newtons, then K, Q1, Q2, Q3 over R squared is going to give you an extra coulombs. It's going to give you newtons times coulombs, and that's not a unit for force. So that's not going to work. Dallas nailed it here. Dallas said, we're going to end up subtracting or something, the forces here. Basically, what we have to do is treat this almost like a physics 20 problem. Remember back in physics 20, when you saw a question that had more than one force acting, you had to draw a free body diagram. Remember that? Remember you did the elevator questions, you did the pulley questions, you did the inclined plane problems, the hill problems, and so on and so on and so on. You did a million different kinds of problems where there was more than one force acting. Vertical circular motion, normal force and force of gravity. Lots of different problems where there was more than one force acting. In every single one of those problems in physics 20, you drew a free body diagram. That's what you're going to do here. Look at object B. Object B, pretend object C isn't there for a second, okay? In fact, so let's cover it up right now. Object B and object A exert a force on each other. Now, we don't care what the force on object A is, because we're not trying to find the force on A. The question says, what's the force on B? So, which way is B affected as a result of A? Well, one's positive, one's negative, right? They attract each other. So let's look at my fists here. Object A, object B. If they're attracted to each other, which way does B go as a result of that attraction? Which way does B go as a result of that attraction to A? Towards A. It goes to the left, right? So we're going to say the force of A on B is to the left. B is pulled towards A. Now, somebody might argue that A is also pulled towards B, right? It is. That's right. It is pulled towards B. But I don't care about that here because that's not the question. If the question said what's the net force on A, then that would be important to me. My FAB, my fab force, is towards object A, toward the left. Now let's take a look at the other one. Let's pretend A isn't there. B is a negative value, C is positive. They're going to attract each other, right? Which way is B going to go as a result of C? Right or left? It's going to go to the right, right? It's pulled towards C. Now, call that FCB. If the other one was my fab force, then I guess this is my force, FCB to the right. Now, there is a force acting on object C that's pulling it towards object B, but that's not the question. The question says, what's the force on the negative charge or the force on object B? All right, what do you think the next step is going to be? I'll give you a hint. The next step is the easy part. Yeah. Yeah, get those two forces. Get those two forces. FAB is KQ QA, QB over R squared. That's 7 point. What is that number there? 2.1, right? And we divide that by the distance. What's the distance we're going to use here, though, for FAB? I'll give you a hint. It's not 3.3. It's half of 3.3 converted to meters, right? So it's 1.65 centimeters. Convert that to meters, we're going to get 0.0165 meters. Let's do that together on our calculator here. Let's say 8.99 times 10 to the 9 times 1 times 10 to the minus 6 times 2.1 times 10 to the minus 6. Doesn't matter if that's a negative value. And then let's divide that by 0.0165 squared. 69.344 newtons. Now, FCB, I'm going to do a lightning fast calculation here and determine what FCB is. We're going to get about 104 newtons for FCB, going through the same process. But it's opposite direction. Right, you got that? Still working on it? Sorry? 104.17? So that's close. How did I do that, by the way? 0.17? Oh, that was really close then. How did I do that in my head? So there's always a trick when I do something like that in the head. It's always a trick. All we did was multiply that by 1.5, right? Because if you take a look at A and B, the charges are all the same here, except for this is 1.5, this is 1. So it should be, the force should be 1.5 times what the first one was, right? So that's a lot easier than doing the whole thing in your head. Okay, what next? What now? Subtract them? Yeah, we want to add forces together because that's what we do when we find a net force. But in the end, we're adding a negative value, so it ends up being the same thing as subtract. We'll say the net force is equal to the sum of the forces. That's FAB plus FCB. FAB is a negative value, negative 69.344 newtons. And FCB is a positive value, 104.017 newtons. When we add those together, we end up getting 34.6522, 672. And it's a positive value. We're going to round that to 3 digits, 35.7 newtons. It's a positive value, so what does that mean about direction? It means to the right. That makes sense? That's not much harder than what we've been doing, right? A little bit, but not much. Okay. Important thing is draw the free body diagram. Find out which direction the forces are in. Don't skip that step. Okay. I don't know how many people. Hold on for a sec. I don't know how many people have done that, guys, in the past. They say, I don't need to do that. I'll just calculate the values and then add them up, subtract them, whatever. Draw the diagram. That's what helps us to visualize the fact that we've got one to the right, one to the left. And that one is going to be a positive value, one's going to be a negative value. Okay? Just one second here, Katie. Your homework, guys, tonight, page 533, questions 1 and 2, please.